Hi, this is Dr. Gutierrez, and welcome to Chapter 3, Section 2, Measurements of Variation. Alright, so we have several different ways that we can look at variation, and the equations that we use are going to depend on whether or not we are looking at a population or whether we are looking at a sample. In most cases, we will be looking at samples. Alright, so how can we look at this? We can look for a range, a standard deviation, or a variance. These are three different things, meaning three different ways that we can measure how spread out the data is. We want to not only know how to calculate these, but understand what they represent. Now, round off rules for the measurement of variation. Variation, you want to do one more decimal place than is present in the original data set. There are reasons for this, but we don't really need to concern ourselves with that. One more decimal point, and that should be fine. All right, range. Range is very easy to calculate, and it is indeed the easiest to calculate, and it gives us the maximum data minus the minimum data. It is not too terribly useful for the most part. It doesn't give us a good idea of how the data is spread. It just gives us the difference between the extremes. This can be useful if we're looking to see how wide the graph needs to be. But if you want to know if it's a very widely spread data or if it's very concentrated, this is not as useful. Okay, the range is also not resistant. Remember that resistant means that an outlier will not affect it that much. Since this uses just the extremes, outliers can very much make a difference here. Alright, since it only uses max and mins, it is going to very much depend on those outliers. Alright, so let's take a look at the range. We've got our Verizon data again. Remember, Verizon is better than the other guys. Megabits per second, not megabytes per second. We want to look at what the maximum of that one is. So maximum is going to be 55.6. We got that right here. Minimum is going to be 14.1. And so the range will be the maximum value minus a minimum value. 55.6 minus 14.1 gives us 41.50 megabits per second. Now, let's take a look at that data again. I'm going to go here. That should be what we're looking at. And here's the data here, and it's already ranged from minimum to maximum. But let's say it's not. And let's say we don't want to arrange it because there's a reason we may not want to arrange it. It could be that we have multiple lines of data. And let's say we want to know what is the minimum of this data here. Obviously, it's 14.1. But let's look at a code that we can use if we are using Excel. Remember, Excel can be a very good friend of yours. So the minimum Verizon speed is going to be, and I'll just put it under here, equal minimum, MIN, open parentheses, all this data, just put it together in here, close it, and enter. So minimum is 14.1, which we already know. Maximum equals maximum. Let me put a title here. So let's say maximum Verizon speed. I can put that in here is equal to maximum of, again, we look at all this data, close parentheses, that will give us our maximum right there. Next, we can look at what would the range be, and let's say the range of Verizon. So what I'm going to do here is, I don't think there's a range function. No, not really. All right. What I'm going to do is I'm going to set up an equation here. I'm going to say equal to the maximum of this data. All right, collect it like that, minus the minimum of this data. So we can use multiple functions all together. And that'll give us 41.5 megabits per second. All right, so that's the range. Next, we can look at standard deviation of a sample. Standard deviation is usually what we talk about if we're talking about how wide a data set is. And very often we will say our data is X bar plus or minus RS. And that is how data will be presented. Okay, so that'll be the standard deviation of a set of sample values. S, for a population, it will be sigma. Now, remember I talked about sigma being that big M on its side looking thing? That was capital sigma. This is a small sigma, and it looks like an O with a little line going across it. So that is a sigma. And these are the lovely little things we have here. Standard deviation of a sample. S is equal to the square root of the sum of x minus x bar squared over n minus 1, or a shortcut formula for standard deviation used by calculators and such is S equals the square root of n times sigma x squared minus sigma x quantity squared divided by n times n minus 1. Let's take a look at this formula for a second here. Let's not just accept it and move on. Now, we are looking at how wide we want to know. Basically, we're looking at what would the average, or what we would like to think about is roughly how much are most of our data points away from the center. Now, we could just say, well, why can't we just say the difference between each data point and add it up? And let me tell you what I'm talking about. So let's undo here. I am actually going to get a new Word document. So here we have our new Word document here, document 2. Document 1 has been used up. And here are our old Verizon speeds. Now, one idea you might have is we could simply say that it is the average of the difference between the mean and each of the data points. So, this might seem like a bit more intuitive of an example, or of a my apologies for the pause. Apparently, I forgot how to use the English language. So, we might want to have a more intuitive idea of how to measure the spread of a data set, how wide apart the data is. So let's say we want to have simply the average of the difference between the mean and each of the data points. So I'm going to call this S sub P, spread. And this is something I am defining. This is something that would be intuitive. This is not an equation you are going to be using on any tests or on any homework. This is just an idea of how would I think intuitively I would measure the spread. And it's just going to be the average of the distance. And so let's take a look. So the distance is simply going to be equal to x minus x bar divided by n. So that is the average. And it's actually going to be the sum of the x minus x bar. So let me go ahead and I will insert. Equation tools. I think I actually just had that. Go ahead and put that as sigma. Boom, right there. Sigma of x minus x bar. Divided by n. And let me go ahead and put that in parentheses, just so we're doing that. So this is the difference. And so we add up all the differences and divide it by n. Well, let's see what happens when we do that. So I'm going to put this equation over here. And well, in order to use this equation, first thing you got to do is calculate what the mean is, or the average. So average, and we've calculated this already, but I'm going to go ahead and do it again, is equal to the average of this So that's going to be 30.75. And this here is going to be x minus x bar. And so that will equal this minus this. So that'll give me negative 16.64. All right, let's go ahead and take a look at that. Now we can copy and paste that here. All right, so the first one seems fine, but look at the second one. 22.4 is the same as 22.4. 23.1, 23.1. Well, see, this obviously is not correct. So let's take a look at what happens. So for the first one, I have A2 minus A9. So A2, this one minus that one, A9. Perfect. But when I go down one, it goes to A3 minus A10. So it subtracts this one. I want it to stay here. And so one of the ways that you can tell Excel that you do not want to go down or up, you want to keep that particular row, is that, let me go here. I will go up here, and instead of A2 minus A9, I'll say A2 minus $1. Now, the dollar says I want to keep that 9 and 9. So I'm going to go ahead and copy that. And then that'll be Control C, and I will Control V, paste it, and now I have A3, A4, A5. And notice that as I go down, the first number will increase by 1 each time, but that 9 will stay 9. So that'll be x minus x bar for all of those. And here I will have the sum, not the sim, the sum of x minus x bar, which is going to be equal to all this. And that gives us 0. And it turns out that that will always give us 0 because we have some that are above the mean and some that are below the mean. And actually, if we take this and separate it and do some calculations on it, we'll find out that this, as this is defined, will always be equal to 0. So that is one of the reasons why we do not do that. And that is why we use this equation right here, which is simply that S is equal to the sum of x minus x bar squared divided by n, and then we take the square root of that. But instead of n, we do n minus 1. Okay? And that's another question that we might have. And the reasons for the n minus 1 are much less intuitive. And for now, I'm going to say it's a little bit beyond the level of this class. If you want to look it up, it is an interesting problem. But I don't want to spend too much time on that. Now, sometimes they'll say it's simply a fudge factor because you are... because it gives you a bit more accurate of a number, but that's not a really good explanation. The explanation actually has to do with something called degrees of freedom. So this will be our answer here. Now you will notice also, if we go back to here, that it said it's going to be sigma of x minus x bar squared over n minus 1, or it could be given by this formula here. S is equal to square root of n times the sum of x squared minus the sum of x quantity squared. And so we could use either one of those. All right, so let's take a look at what we would get for this one, which would be the same as this one. So back to our Verizon. So instead of x minus x bar, I'm going to do x minus x bar squared. So that will be, and let me just change the label here, x minus x bar squared. And so each one of these will simply be equal to this minus this squared. So I will copy that and paste it all the way down here. This gives us our sum here, and S will simply equal to, it's going to equal to the square root, SQRT, of this number, sorry, okay, let's try that again, equals SQRT of this number divided by n minus 1 is 1, 2, 3, 4, 5. 5 minus 1 is 4. Alright, so that will give me 16.45 as our standard deviation. Apologies for my throat. My throat's a little dry. Now, one other thing I wanted to go over, and I'll try to do it quickly, but I will leave the calculation, a paper copy of the calculation if you want to take a look at it. So we have this S equals square root of da-da-da. Shortcut formula, doesn't really look that short, but it actually is. S is equal to square root of n times sigma x squared minus sigma of x quantity squared over n times n minus 1. And remember, the capital sigma is a summation. So we are looking at S and, well, S. So let's go ahead and take a look at that calculation I promised you. So here we are. It's going to be slide 49 proof. We start with S equals the square root of sigma x minus I, or x of I minus x bar, quantity squared, over n minus 1. So a couple of things you want to remember before we continue on. We want to remember that when we have a binomial, a plus b quantity squared, that is equal to a squared plus 2ab plus b squared. And x bar is, by definition, the sum of x sub I over n, and this implies that the sum of x sub I is equal to n times x bar. All right. Therefore, S is equal to sigma of xi minus x bar squared over n minus 1, which is equal to the sum of, square that out, we get x sub I squared minus 2x sub I x bar plus x bar squared over n minus 1 equal to square root of sum of xi squared minus 2x bar sum xi plus sum of x bar squared. Now, sum of x bar squared is equal to n times x bar squared. And that's because we are still adding this up, even though it's just a plain number, over itself n times, because we have n items. Equal to the square root of sigma xi squared minus 2x bar times n plus n times x bar squared over n minus 1, summation of xi squared minus 2n times x bar squared plus n times x bar squared over n minus 1 equal to the sum of xi squared minus n times x bar squared over n minus 1, because we have two of these here, we got one of these here, so minus 2 plus 1 gives us just minus 1. And now I'm going to multiply that by n over n, which is just 1, so that's not going to change the value of the quantity. Now this is equal to n times the sum of xi squared minus n squared times x bar squared over n times n minus 1, and this n squared minus x bar squared is going to be n times x bar, quantity squared, and n times x bar is equal to the sum of xi, so that will simply be the sum of xi squared. So that gives us n times the sum of xi squared minus the sum of xi quantity squared over n times n minus 1. So that means that we have these two equations equal to each other, which is what we had here. Alright, if none of that made sense, don't worry about it. You can just accept the fact that those two are equal, and you can use that. Or, if I spoke too quickly, and I do sometimes tend to have that tendency, good use of words there. I'm great. All right. I will upload a PDF of this so you can go through it slowly and take a look if you want to. All right, so let's go ahead and continue here. Now, the standard deviation is a measure of how much data values deviate away from the mean. Right. So S is never 0, or it can be 0 if all the data is the same, but it can never be negative because it is a square root. And we are only taking the positive values of that square root. Larger values of S indicate greater amounts of variation. So, if we have a lot of outliers, S can increase dramatically. This means that it is not going to be very resilient. S should also have the same units as the original data values. If we had dollars, they should be dollars. If we have pounds, they should be pounds. All right. The sample standard deviation is a bias estimator of the population standard deviation sigma, which means the values do not tend to center around sigma. All right. This is giving us exactly what we had before. X bar is equal to 30.7. Sum of all that. Alright, n minus 1 is 4. Plug it into Excel like we had it. And that should give us our S of 16.45 megabits per second for Verizon. Alright, good range rule of thumb. It is crude but simple tool for understanding and interpreting standard deviation. The vast majority of your samples will generally lie within 2 standard deviations. And this will be in distributions that we call normal distributions, and you will become very familiar with those as time goes on. There we go. Sigma. Values that are within 2 sigma are not very significant. So, a value that is below mu minus 2 sigma would be considered a significantly low value. One that is above mu plus 2 sigma would be considered a significantly high value. And those that are between negative 2 sigma and plus 2 sigma are not going to be considered significant, or at least that they do not have a significant variation from the mean. Again, we could be talking about heights here. If you are within 2 standard deviations of the average height, you're not going to be considered really tall or that short. On the other hand, if you are above or below those limits, then you would be considered tall or short, as an example. Another good rule of thumb is if you don't know the standard deviation, you can take the range and divide it by 4. Very crude, but if you're looking for something that's what's called quick and dirty, that could give you a number. Now, if we are looking at the population standard deviation, which is a parameter rather than a statistic, we will have sigma is equal to the sum of x minus mu squared over n. Now, this is not n minus 1. This is simply n. And that is a significant difference here. Like I said, it's a little bit beyond the level of this class to say why for a population we have n minus 1. Or sorry, for a population we use n, and for a sample we use n minus 1, but it does have to do with degrees of freedom. Now we can also talk about the variance of a sample or population, and this is simply equal to either s squared for a sample or sigma squared for a population. So basically the same equations we had before without the big square roots. So S, sample standard deviation, S squared, sample variance, sigma, population standard deviation, and sigma squared, population variance. All right, the units of the variance are going to be squared of the units of the original value. So if, for example, we were talking about dollars and the average price of dollars and the standard deviation of the price of dolls at a certain store and the variance of a price of dolls, assuming we're buying them in the US, so we'd be using US dollars, The variances would have units of dollars squared, which doesn't really seem to have too much of a intrinsic idea in our heads, but those would be the units. And unlike standard deviation, the variance will be considered an unbiased estimator. All right. So this is going to give a hand-waving example of why we divide by n minus 1. I do not like this particular example or this explanation. If you want a good one, you can go ahead and look up on YouTube. There are some that I have found that are good, but most are usually just hand-waving examples. All right. Empirical data with a bell-shaped distribution, sometimes called a bell curve, also sometimes called a normal distribution. So for one of these distributions, data that values, or 68% of all the data will fall within one standard deviation of the mean, 95% will fall within 2 standard deviations of the mean, and 99.7 will fall within 3 standard deviations of the mean. We will talk about how exactly we calculate this later, or I should say how it is calculated. For the most part, we read it off of a table because it involves an integration, which is calculus, and even at that point, it's not something that can be solved by hand in calculus. It actually has to be solved by a computer. So we will talk about z-scores and how we can get percentages from those from a z-score table. Or you can also use technology. I have a TI-89. A lot of TIs will tell you how to get the percentages from the number of standard deviations. This is a good bell curve here. So minus S plus S, 34.13%, 34.13%. Add them together, we get 68. 2 standard deviations, 95. 97 for that. Now, if you want to talk about how much data is above x bar plus 3s, you're looking at a very small percent, about 0.13% of all your data will lie above that. Similarly, 0.13% of your data will lie below x bar minus 3s. Right. You're going to be very familiar with this curve. This is a normal distribution or a bell curve, but usually it's called a normal distribution. All right, so let's look at this one. IQ scores have a bell-shaped distribution with a mean of 100 and a standard deviation of 15. What percentage of IQ scores are between 70 and 130? Well, we have a difference from the mean to a maximum of 2 S and a difference from the minimum to the mean of 2s. So we're talking plus or minus 2s. We can go back up to here. Minus 2s plus 2s, 95% should be within 2 standard deviations. And we shall get this, 95% of all IQ scores are going to be between 70 and 130, approximately. All right, now Chubyshev's theorem. Now a theorem is a mathematical law that has been proven. That means that using certain logical rules, as well as certain properties of statistics, it can be shown that we always have this. All right, Chubyshev's theorem says that for any set of data lying within k standard deviations of the mean, at least 1 minus 1 over k squared, that the proportion of any set of data lying within k standard deviations is always at least 1 minus 1 over k squared. So that's at least, it's a limit. And k is any positive integer greater than 1. 2, 3, 4, 5, 6, 7, heck, 8. Let's go all out. So, at least 75% lie within 2 standard deviations. At least 89% lie within 3 standard deviations, and so on. All right, Chebyshev theorem will give a limit, but it is best if we know the shape of the curve, and that should be able to give us better statistics. All right, let's go with this one. IQ scores have a mean of 100 and standard deviation of 15, just like we had before. What can we conclude from Chebyshev's theorem? All right, well, at least 75% of scores will lie within 2 standard deviations, or between 70 and 130. All right, so at least. Notice that before we were able to get a better number for this. Also, 89% should lie within 3 standard deviations, between 55, which is a very low IQ score, and 145, which is an awesomely awesome IQ score. If you have 145, you are awesome. Woohoo! All right. So we can also, so here the coefficient of variation, CV, simply will give us a percentage of how big the standard deviation is compared to the mean. So S over X bar times 100, or sigma over mu times 100. Another round off rule for the coefficients of variation. These are not going to be that particularly important for exams, for the midterm or so. You will actually just, as long as you give me a couple of digits, I'm not going to be too terribly concerned about where you round it off. So don't worry too much about that. All right. Biased and unbiased estimators. So standard deviation is going to be a biased estimator, and so this means that the values of the sample standard deviation do not tend to center around the population sigma. All right. The variances are unbiased, which means they do tend to center around sigma squared. All right. And usually what you are trying to look for is you have a sample and you want to try to make conclusions about the general population about it. So this is usually how statistics will work. We want to find out about the whole population, but we cannot get information on the whole population. So we take a sample and try to get as unbiased a sample as we can, and then try to get as unbiased an estimator as we can. Next, we shall be continuing with section 3.